Hi, in this video we are going to see the rectifier, three-phase full wave control rectifier, and we will see the different options. We will see the simulation output for different options. So we have collected this icon from the library browser. So it is a sub-voltage supply which is of, let us take 100 as a VM, peak value of the phase voltage, with a degree of 0 degree lag. Another one we will take lagging by 120 degree, and let us take the peak value as 100 and phase degree lag as 120. So obviously this is RY and this is a B phase. This is 100 and another is phase lag of minus 240 degrees. So what we are going to do is we will just connect these three-phase supply to a three single-phase transformer. These three single-phase transformer we can connect in star delta. So we have to just join this from R dash to Y, Y dash to B, and this B dash to R, right? So this is a delta connection here, and the other side we will make a star connection, and this we will ground over here. So we will take the ground connection and connect it over here, and we can have isolated ground as well. And this R dash, this is Y, so Y dash, this is B, so B dash, these are shorted. And now we have these star terminals, we can take it out. So what we would like to do is that we would like to keep an ammeter over here. So ammeter is one ammeter over here just to measure the R phase current in the star side, and in the delta side also we will keep an ammeter. We will have this ammeter over here, so it will measure what is the delta current, like for inside the delta how the current is going on, what is the waveform. It will measure the current in the delta end, and also we will have another ammeter which will measure the current from the supply end, right? So from the supply end we will connect the R phase, then Y phase will be connected to the Y terminal, just like the R phase is connected to the R terminal through an ammeter, and we have a B phase will be connected to the B terminal. So we are taking just ammeter in only the case of R. So R phase current, and here the output current we will try to measure. So on the other end of these two we will short. So the input of this three-phase supply is shorted, and we can take this ground here. We will connect this ground terminal also here. So the supply end, this is grounded, it is connected to the transformer three phase now, where it is primary is connected in delta and the secondary is connected in star. Okay, so now we will just take this ammeter from here out. This is now star delta connection. So here we will take it to the one leg. This leg is between two thyristors. So these two thyristors T1 and T4 is in one leg. Another we will connect these two. So let me just connect this one with Y, and here we will connect here this one. So we have got RY, and another one is we will connect to B. So let it connect like this, and here we join with R, Y and B. So in the three phase the input is AC, so it is going inside of it, to the anode terminals, and the cathode terminal is taken out. So let us put an emitter in the output also to measure what is the DC current. So let us connect this here, and now we will connect this to the load, and load will be taken out from here, and this will be connected to the all the legs, right? DC will be connected from the top and the bottom. So here all the three, like this is a three-phase inverter with all the thyristors are connected, and gate pulse is kept it open. So we have already made the gate pulse for all the thyristors. So these gate pulse are given by the calculated values. How much is to be gate pulse is given, so accordingly we can give the firing pulse over here. Now we have set the firing angle as 0 degree. Right, and this is a freewheeling diode. We can connect, or we may connect later on. And let us keep the voltmeter in appropriate place. So voltmeter, we'd like to measure what is the phase voltage. So first we connect this to R phase, and another one we will connect to the ground. Another one, the input side, we'd also like to see what is the line voltage. So we connect this to this voltmeter to the line value between R and Y. So we are measuring the R phase and also RY. Similarly, in the output, we would like to measure, this is a star connection in the output, so we can measure what is the R phase voltage. So R phase will be from R and the ground. Also, we would like to see what is the output voltage between R and Y. So let's connect it between R and Y. So these two are connected. And last, we would like to see what is the output voltage across the load. So let us keep it here. So correct. So this is our circuit is over. In the lab, we have a three-phase transformer. Isolation transformer is there. The supply is given through a three-phase variac, and here we are not adding a variac anyway. So here we are giving a three-phase supply. Three-phase supply is given to the three-phase transformer. Primary is delta, secondary is star, and these three input are given to the three legs of a three-phase to DC rectifier, and the output is we have a load of resistive load, and this freewheeling diode we can connect, or we may leave it open and see that what is the output voltage. And here we have got the scope. So we have taken, let us take two scope from here. So we will see the currents and all. So 1, 2, 3 currents, so emitters over here. So we first will see the input current, then we will see the what is the current in the delta, which is formed, what current is flowing in this delta. Then we want to see what is the output current, also current in the R phase. So input current in the R phase, what is the current in the delta, what is the current in the output of a star. Then we would like to see the load current. So that's all. These four currents we want to see that first. And here we would like to see in this scope the input voltage. So let us say input voltage, then we say input line phase voltage first, then line voltage, then again the phase voltage, output, then our output line voltage, then the load voltage, right? So these five we will see here, and these four currents we will see here. So now what happened is we will simulate it, and the simulation time is up to 0.1 seconds. We can see 5 cycles. Let us run it. So after running this, we can see that the current in all. So here comes the current waveforms. So here is the current waveform. So let me write down what are these currents, and then I come back to you. Now when we give a gate pulse and we run the simulations, so what the output voltage we are getting, let us see. In this, the output voltage, the first one is a green one, which is the input phase voltage, the R phase. So obviously we have taken the Vm as 100, so this is 0 to 100 and that's all. And then we are giving the, let me just keep the simulations aside, which will be helpful to understand. Yep, so here the simulation is. So as we see, the input phase voltage is the green one, which is starting with 0 with the Vm is 100, and like that it is making a 2 pi 1 cycle at 0.02 seconds. That's very good. 0 to 0.202 seconds we are getting a one full cycle, right? Then we are measuring between R and Y. Obviously this R and Y is the line voltage which leads the phase voltage by what degrees? 30 degree, right? So here we can see that this R and Y, this leads by 30 degree, right? That is why blue line is something a little higher, it is there. So it is leading it, and we know that line voltage is root 3 times of the phase voltage. So phase voltage peak value is 100. This is 100 root 3, that is 173. So around 0.5 you will get here. So this is the line voltage, right? So this is the line voltage. The input is delta connected. So between any two winding we have R phase terminal. So we have 173 volt, the peak value. Now when we go for the secondary side, obviously this will be 1:1 transformer, so we will get output also same 173 volt. But the output is apart from the output is we can measure the phase voltage also, we can measure the line voltage. The phase voltage, when we are measuring, it is measuring between the two terminals, the terminal 1 and terminal this terminal. So since it is a star connected, the phase output voltage and the phase voltage of this between the winding will be same 173 peak, and the line voltage will be root 3 times of the 173, that is 300 volts. So what we can, this red line we are getting 300 volts. So we are getting the input peak is 100, then output the input line voltage as 173, secondary primary of a transformer, secondary of a transformer 173, no phase change. Yes, when we see the secondary line voltage, again it is phase change of 30 degree. So this is already 30 and this 30 becomes 60 degrees. So there is a phase change of 60 degree we get here, right? So this is about these 4 voltage waveform, the green, blue, 2 blue and the red one. Also in the output voltage of this blue we find some notches over here, or these point notches are there, these which is also reflected in the line voltage, these notches of small notches is there. So since we are starting with the pulse, we are getting some not a right one. So let us do one thing. We see the waveform exactly at from 0.02. So let us see the waveform from 0.02. How many cycles? Let us see it for the 2 cycles. That will be fine. Okay. Now it is exactly for 2 cycles. We can see that. But it would be better if I can just take from here. Let us see this one this way. Okay, so it should be starting with this is from 0 here upwards. So we would like to also see that what happened in the previous one. So that's why we just take a little bit ahead. So 0.02 to 0.04 seconds, this is the 1 cycle, and we can see the output voltage 1, 2, 3, 4, 5, 6. 6 pulses are there in the output voltage. and this is the simulation, right? So let us in the simulation, where is the output voltage? Voltage is here. This freewheeling diode is not connected, and we are seeing the output voltage like this. So this is what we get, right? And what else? Another difference we observe is that is like if it is starting with like of the green one is at 0 degree, the blue one is leading by 30 degree, the secondary of a transformer same leading by 30 degree. However, this red one you can see it is leading by 60 degree. And the observation next is that the output voltage, it is following the output line voltage. So this red one is the line voltage, right? So red one is the between R and Y. So this output voltage is following the output line voltage during this time. So this value is matching, this blue one is matching with this red one. And the output phase voltage is this blue one, right? So if you say that if this is a R phase at 30 degree, it is the R phase is maximum. R phase is maximum with the T1 as a thyristor, and it is maximum from 30 degree to 100. This is the R phase, 30 to 150 degrees. So between these two times, this R phase is maximum. So when R phase is maximum, at that time only the firing should be given, right? If you give the firing pulse at this particular instant, then we can get the small dip over here. Again, it will be falling. To know this, all those things, let us change the firing angle from 0 degree to let us say 30 degree. Let us suppose. Let us give the firing angle 30 degree and see the waveform again. So we fix the firing angle to 30 degree, and let us run the simulation. At the same time, we can see the change in the output. So here we see the change in the output. So let's see the changes from 0.01 seconds to some cycles. Yes. So cycle is starting from 0.02. So we can see that this blue one should be following this red one, right? And what we find is this is deep blue. So this is not there. From 0 degree to 30 degree, there is a lag, right? Initially, this one is output voltage is following completely the red one. Now from 0 to 30 degree, we can see here 0 to 30 degrees, the firing is at 30 degree. So up to 30 degree, the output is not there, but after 30 degrees, it is following the red one. And same pattern is there after like up to what degrees will have, because this is our input is like phase voltage, the output phase voltage from the star connection. So 30 degrees here, and this 30 degree will be there till this up to 150 degrees, this will be there. Right, so it will be there till 150 degrees. So till here. So we cannot see that one, because that will again the following the another line voltages. To understand that, if we have the 3 voltages over here, then we could have understand that. But for now, being it is important that here the output voltage is the deep blue of this. This was following the red one, right? And then let's see the current waveform. Oh, the current waveform is the very distorted one. It is like if I zoom it from here, from 0.02 seconds we should have a waveform. Okay, waveform is here, so let us zoom it from the previous, as per the previous way. Yes, so from 0.02 seconds we can see this is the output current. The output current is the same as the output voltage because of resistive load, and you have the this like this. What we will do is that let us change this firing angle from 30 degree to 0 degree, and then see that what is the simulation output look like. Okay, this simulation output is quite easy to understand. We can see that this output is the line current. The R phase current is from 0 to 120 degrees. The R phase current is active, and again 30 degrees is off. From 180 degrees again for 120 degrees is on, then it is off. And in the delta side the same current is there, but when we see the R phase current is look like this one, right? So that's the difference, and output current is a cap over here. So just because it's a resistive load, you will get a cap on the output side. So this much.